Okay, so we start with static structures. So double click on static structures. Then material we use static what you call structural steels. So under geometries, I think you have to we use space claim. If you referring to tutorial is space claims. So if yours is default is discovery geometry, so what you can do is you go to tools, options, right? Geometry imports. Under geometry import, you can change to preferred geometry editor is space claim. Okay, space claim direct modeler. Okay, you can do this. Okay, default it should be if you haven't changed it, it is the discovery. So I changed to space claim direct modeler. So every time when I click this, my default is space claim. So I double click this, then it will start with space claim. So you can see here is starting space claim. Okay, then we can start draw the L-shape brackets. Okay, L-shape design. So before we start, you can actually look at here space claim options under file options. Then you have this unit. Probably you have to ensure this is in millimeter. Then you can use the grid is 5 mm. So easy for us to draw the brackets, L shapes. Then you can start sketching. So okay, select a new sketch plane. Then we are in XY plane, right? So click on XY. Then we can now draw. You can choose the Z axis at here. Okay, then we can start drawing. So the line. So we start from this origin. So I think the base is 35. If you check back your tutorial, okay, the case studies. So seven grids. 7 grid is 35. Then here is 15. Can you cross check? Then here is 20. Go up 20. Then here is 15. Then come back to 35. So this is my L shapes. Okay. So once you have done this, okay, then you can select pool, right? Pool to a thickness of 2 mm. Okay. Then you click pool. Okay. Then you pull it 2 mm. Oops. Control Z if you want to back. Okay, it's 2 mm. So to make sure this is correct, you can do measure at here. 2 mm. Right? So my thickness is 2 mm. So this is basically done the model. Okay, all can model it. Can. Okay, I will wait for another while. So if this is done, then you can close this. Basically, it will auto save. If you go back to your geometry, now you have a tick here. Then you can go to model. So when you click model, it will start mechanical here. You'll see here, it will start mechanical. So now I will, mechanical. it will upload the model. Yeah, so I have this model out. Material is structural steel. Mesh, I put 1 mm, if not mistaken. Okay, so you can generate the mesh. So it will look like this. Then you, under structural here, you have to import the fixed supports. Put a fixed support on top surface. Then a force, downward force at this edge, right? So we have to put in right click, force, okay, select this edge. We put components force, which is -300, so it's moving down. Okay, then we insert total deformations and stress, equivalent stress, then we can solve it. Okay, the stress is 821.35 megapascal. The deformation is 0.09, right, mm. Okay, so that's the first part done. I will stop the record. I turn on ANSYS workbench. Okay, so we start with static structures. So double click on static structures. Then material, we use static what I call structural steels. So under geometries, I think you have to we use space claim. If you referring to tutorial is space claims. So if yours is default is discovery geometry, so what you can do is you go to tools, options, right? Geometry imports. Under geometry import, you can change to preferred geometry editor is space claim. Okay, space claim direct modeler. Okay, you can do this. Okay, default it should be if you haven't changed it, it is the discovery. So I changed to space claim direct modeler. So every time when I click this, my default is space claim. So I double click this, then it will start with space claim. So you can see here is starting space claim. Okay, then we can start draw the L-shaped brackets. Okay, L-shaped design. So before we start, you can actually look at here space claim options under file options. Then you have this unit. Probably you have to ensure this is in millimeter. Then you can use the grid is 5 mm. So easy for us to draw the brackets, L shapes. Then you can start sketching. So okay, select a new sketch plane. Then we are in XY plane, right? So click on XY. Then we can now draw. You can choose the Z axis at here. Okay, then we can start drawing. So the line. So we start from this origin. So I think the base is 35. If you check back your tutorial, okay, the case studies. So seven grids. 7 grid is 35. Then here is 15. Can you cross check? Then here is 20. Go up 20. Then here is 15. Then come back to 35. So this is my L shapes. Okay. So once you have done this, okay, then you can select pool, right? Pool to a thickness of 2 mm. Okay. Then you click pool. Okay. Then you pull it 2 mm. Oops. Control Z if you want to back. Okay, it's 2 mm. So to make sure this is correct, you can do measure at here. 2 mm. Right? So my thickness is 2 mm. So this is basically done the model. Okay, all can model it. Can. Okay, I will wait for another while. So if this is done, then you can close this. Basically, it will auto save. If you go back to your geometry, now you have a tick here. Then you can go to model. So when you click model, it will start mechanical here. You'll see here, it will start mechanical. So now I will, mechanical. It will upload the model. Yeah, so I have this model out. Material is structural steel. Mesh, I put 1 mm, if not mistaken. Okay, so you can generate the mesh. So it will look like this. Then you under structural here, you have to import the fixed supports. Put a fixed support on top surface. Then a force, downward force at this edge, right? So we have to put in right click force, okay, select this edge. We put components force, which is -300, so it's moving down. Okay, then we insert total deformations and stress, equivalent stress, then we can solve it. Okay, the stress is 821.35 megapascal. The deformation is 0.09, right, mm. Okay, so that's the first part done. I will stop the record. All right, so I will repeat against the parametric optimizations. So after we have done the structural optimizations here, or shape optimization or topology optimization, so what we need to do is just share these results to transfer to design validation system geometries. So, but before you do this, you have to make sure your defaults modelers is space claim. So what you can do is you have to check under tools options to find under geometry input, you have changed it to space claim. 2023 versions, it use discoveries as a default, so you have to change to space claim. So if this is done, then what you can do is transfer your results to design validation system geometry. Okay, I click on this, it will create static structures analysis as you've seen here. So we need to wait for some times to let it create or transfer the results. The whole idea of here is to make sure you have the topology optimized design model, then you recreate this design model for further analysis or further optimization using a parametric optimization. So once it's done, you will see there is analysis, static analysis coming out here. So what you need to do is just update your results in structural optimization or topology optimizations. So it have to update this. It also will take some time. So once it's updated, this is a tick here, green tick, then you have to now go to here, the geometry, to update these geometries. So go right click, updates. So if it's updated, then you have a green tick at here. Now you right click. You can now edit this geometry in space claim. So when you click this, you will be opening the space claimer, right? So under space claim, you will see that's your model. Earlier, the full solid L-shaped model as well as the topology optimized model all appear at here. Okay, under these structures, you can now hide these full structures. Okay, then you can start to remodel these optimized topology optimized models. You can see that because now it's not a full straight line, it have its very not perfect shapes in this case. So the topology optimization is just helping us to have an idea, give an idea how it should look like. So we have to recreate this model, make it better. At least here is refine this line or refine this surface, refine this surface, make it a better smooth models in that case. So now we want to build a 3D model based on what's being topology optimized, right? So before we start, we have to make sure, probably have to check back under the units, we are in the same scale, millimeter. Here we have to put 5 mm so that we have the same scale. Then what we can do now is go to design, sketch mode. Then we select the surface, the top surface, the front surface of this model. Okay, you click on this. So we now doing a sketch on this particular model surface. Okay, so what we need to do is we have to do a box select. So what you need to do is just click on this, drag it, right? We select the entire this surface. Then you have here a copy. We copy all the line of this particular design and we paste it. Okay, so now you have a sketching plane with the design at here. So what we need to do, we can now hide the topology optimized design. Then we have a plane to sketch a new design based on the topology optimized shapes. Okay, we have to smoothen this, make it a perfect line, straight line, like this, straight line. This curve, we have to make sure we make it a straight line. So now we have to try to edit this. So the first thing we can do is we do a repair of this sketch under fit curve. So when we click on this fit curve, it will find the curve, all this curve with point. Basically, it will create under maximum distance of 0.16, it will try to whatever curve it will create into lines. All right. So I found that if you choose to 0.1 will be better. So you have more points to select. Then you can modify this this design from the curve that it generates. All right, so if this is good enough later on, then we can click OK. Then we can start to repair it or modify these designs. Go to Sketch, you have this so-called trim. So you want to trim away all those curves that's not straight line. So we replace with a straight line. So like for example, you click trim, you trim this out, trim this out, trim this, then we can replace with a straight line, right? So it will be better like this. Continue with probably this one we also don't want. We can replace it with a straight line. All right, then yeah, I mean same with this. We don't need this. Then we can continue with probably a straight line at here. Same with this particular parts is so many curve. Yeah, we can also put replace with a straight line. Probably like this. It's better. Okay. Then this part can be also removed. We replace with a straight line. This part can be removed. Yeah, we can replace with a straight line. So it's very individual. I mean, if you have your own choice to select which point to remove, which point to rearrange or to build your model based on what I mean here is the topology optimized shapes. So yeah, it can be your own designs based on what's suggested by topology optimized shapes. Okay. So if this is good, then we can further smoothen this all this curve. We can also remove. So we make our own standardized curve. Okay, you can remove this curve. For example, this one also. All right, then we can go to this create rounded corners. So you can select here, then go point to here, then enter 2, click enter. It will help us to create a 2 mm kind of rounded corners. So same with this, you select this, point to here, select enter 2, enter, it will help us to create this. So we want to make all standardized corners. So you select this 2. Right, select this. Select this one, 9. Then move to here, enter 2. Oops, it have to be correctly selected. Yeah, 2. So you help me to make a 2 mm corner. 2. Right, so it helped me to create a standard 2 mm. Alright, so here also can be done in this way. Okay, so sometimes here also you can do that. Sorry, but for example, this you can also do something like make it as a corner, create corner first for these 2 lines. For example, like this. Then only you start to create corners from here. Probably that is another technique, right? Yeah. So if you think this is good enough, then yeah, we can end the sketch. Right. So we have this surface now where we need to pull it or extrude it to the thickness 2 mm. So what we need to do is, yeah, you click on the surface, then you click on pull, then there is an arrow here, so click on this surface that you want to pull. Then there is a ruler here, click on the ruler. Okay, then click on back on the surface, then click enter, so that you enter the thickness is 2 mm. Okay, so that's come out. So we also need to set this 2 mm thickness as the design variables, the input. So we have to add this, click on this P, so it will add it as one design variable. So when I click on this, then it will group this parameter 1 created. So, right, so you can go to this group and check this is 2 mm and you can rename it as thickness. Right, then you can also measure it and double check whether the thickness is 2 mm. Alright, so if this is done, basically the model is created, a good model is created, then we can continue with the subsequent step, which is parametric optimizations. Right, but before that, if you go back to the what we call the project schematics workbench, then you can see that your results should be giving you have to suppress at here you have to suppress the model, earlier model, only leave one model, right, which is the updated design. Compared to, you can also compare if you want from earlier and now the topology optimized model. Okay, now I have modeled it based on the topology optimized shapes. Okay, if this is good, if you close this, go back to workbench, right? So this geometry become a tick. So now I can rerun this model. Okay, double click, it will go to mechanicals. So it will open mechanicals. So we run this based on yeah. So if you can see, the shape will be replaced with the new designs in that case. So what we need to do is we have to rerun this back. The materials we have to select back as structural steel. Then mesh, we generate back the mesh. Then here we have to select back the fixed supports, which is on top surface, and the force, which is at the bottom edge, right? And we can resolve it. So you can see that our new design having the displacement or total deformation of 0.21 from 0.09 solid L shapes now become 0.0 topology optimized shapes is 0.21 mm. Then equivalent stress is 881.37. All right, so that is the parts up to you remodel the L-shaped brackets based on topology optimized shapes using space claim. So now you have a new model. Now we can further optimize it using parametric optimizations. If you refer to the questions, with these topology optimized models, we want to perform parametric optimization to further reduce the weights of these brackets, at the same time to ensure that this deformation or total deformation does not exceed 0.3 or below 0.3 mm, right? So we need to set our output or our state variables. In this case is the total deformation. So maximum, we have to create total deformation maximum. We have to make it our parameters or state variables. At the same time, the mass of this, which is 0.004 kg, we have to set it as our state variable or the outputs, right? If you can see in our workbench, right, project schematics, then it will create this parameter set, which is you have the inputs, which is the thickness, output, which is the total deformation and the mass. So if you double click on this, you will see the input and outputs, one input and two output. So because I have the previous result, probably not to confuse you, I will remove this totally. So you can now have a better view of the entire results. Okay, I remove this. So it will look like this. So you have the double click on this, right? You have the input thickness one, and you have the what we call the output, which is total deformation and system solid mass. Okay, 0.00004. Okay, so that's basically combined. So next is to perform parametric optimizations as required by the questions. So to perform parametric optimization or response surface optimization, you have to go to here under design explorations, response surface optimization. So if you have these parameters set in and out, what you need to do is just double click this response surface optimization. It will connect this to your parameter settings at here. So what we need to do is double click, right? So that it create out this response surface optimization connect to these parameter sets, right? So what we need to do now is to set up this DOE, then response surface, then before we can perform optimization to find the best candidate that fulfill the design constraint. So in this case study, the design constraint is minimize the weights plus ensure the response, which is total deformations not more than 0.3 mm. Right. So what we need to do, we have to start with a design experiment. Double click on this. So under these settings of a design of experiment, we have to ensure we keep this design point info. At the same time, the design experiment, we use CCD, Central Composite Design, like I mentioned in the what we call lectures just now. Then we have to also find these design types to face centers, define it as face center. So we are using face center CCDs. And the setting is up, then we have to look into the design variable, our inputs. We have to set a bound, a limit for these design variables from what to what it can change. So the thickness is our design variable. So we put our lower bound is 1.5, upper bound is 2.2, meanings, yeah, I can allow the optimization later on to change from the input or design variable, the thickness from 1.8 to 2.2 to find which one is the minimum weight and the deformation does not exceed 0.3 mm. That is the bound that you have to take notes. So every optimization, parameter optimization, you need to have this lower and upper bound defined, so that you don't optimize with a very large bounds in that case. So you can put 1.8 to 2.2. We use the default for this case study. Then yeah, you preview the design point, or what we call the input variables, using the face center CCD. So in this case, only 1, 2, 3, 4, 5, 5 levels. So you have one input or one design variable, 5 levels. So of course, using face center CCD also will create a total of 5 design points. So you have 1.8, 1.9, 2.0, 2.1, 2.2. So what you need to do now is you have the inputs, 5 level inputs. You have to rerun everything back to find the total deformations and the mass, the outputs of these inputs. So we do updates. Remember, this is the process of, it will take a very long time, right? So if I were you, I would suggest you to, during this time, during your final exams or final assessment, you can leave it to continue to run, and you can focus on your manual calculation parts, right? To complete another questions while waiting for this to complete. So imagine now you have only 5 design points, right? If you have 2 design variable or inputs, then the combination you have more, then probably it's not just 5, maybe 10, 15, or more than 15. So you imagine you have to run the simulation 15 design point 15 times, right? It will take quite some time. So you have to yourself also have to optimize your times in solving the problem during the final exams. Okay, so you can see that it have completed earlier the current thickness, which is 2. Then it start with 1.8. You found that this is the deformations. Doesn't exceed also 0.3 mm. Then the mass is reduced. So we will look into other design points. Of course, this is quite straightforward. So you can immediately see which one is the design point, which design point can fulfill your design constraint or the criteria, right? So, but assuming you have many design variables, inputs, 2 or 3 inputs, and you have 2 or 3 outputs, then the relationship become more complex. Then to find the optimum inputs or design variables, you may need the response surface modeling as well as the optimizer to help you to find the optimum candidates. So let's treat it as, this is the procedures. Now I do not know which one is the optimum thickness that fulfilling the design constraints. Then I have to perform a full response surface optimizations. Okay, if this is completed, after a while it have completed, right, all completed, then you go back to the project schematics, you will see a green tick at design of experiments. Then you go to response surface, the second steps. So under response surface, we have to also preserve the point for optimizations. And you have different response surface types. Earlier versions, earlier ANSYS version, they are using these standard second order polynomial functions to build the relationships. So now the default is genetic aggregations. So we use the default genetic aggregations. So what we need to do is just updates. Once the settings up, then we click updates. So with the input and output from the DOE, design of experiment, now I can build the relationship through response surface. So it is done, all tick, then you can look at the response point, this response. Because this is just 2D, you have only one input, right? It cannot plot something like surface. If you have two inputs, then you can plot 2 inputs over 1 output, then it can plot a surface graph. So now it's just a line, and it tells you the relationship of thickness and total deformations. Thickness increase, deformation decrease, and it will also tell you the mass, thickness increase, the mass increase, the relationship. So later on, the optimizer will basically based on this relationship that it have built through response surface to find the best candidate that fulfill your design constraints, right? So now this is done, and you go back to project schematic, you have a second tick at here. Then now you can go to optimizations. Double click on this. The optimization, you have to do some selections, settings. At here we do a manual, and the methods we just use screenings. There are other algorithms to use for optimizations. So in this case, we are just using screening. We find the 1000 number of sample and find the best 3 candidates. So now we have to set the objective functions. So first is the deformations. The deformation, we have to ensure that it is below 0.3, all right, mm. Then the second one is the, what we call, this is a design constraint. The second one is the objective function, which is minimize the mass. So we do a minimization of the mass, right? So if this is done, then you can update. So if you look at one is done, a tick here, you can look at this. It tells us that, candidate number 1 fulfilling the best candidates, which is 1.8 thickness, giving you the deformation less than 0.3. At the same time, this mass is the minimum mass compared to others. Okay, of course, there are candidate number 2 and candidate number 3, which is 1.84, 1.88. So 1.8 is already a design point just now, right? In parameter set, 1.8 is already there. Okay, 1.8 is already there. So what we need to do is, we have if you think you want other candidates, for example, for example, at here, you want other candidate, what you can do is right click here, insert as a design point. If you click on this, under your parameter set at here, you will see this. All right, but now we are focusing on 1.8 because it's the best candidate. What you need to do is just right click, update. Basically, you have to copy input to currents. So it will replace the design point of the current design point from 2 mm to 1.8. So what you need to do is just update this. And once it's updated, your entire design, entire analysis earlier at the project schematic, your mechanicals, your design in space claim, your analysis result in mechanicals, all will be updated based on the best candidate, which is 1.8 mm thickness. All right, so let it updates. Then we will see how the final results look like. So if this is done, then you can go back to here and open space claim as well as mechanical to see the final results, the updated design. So I can double click on it and double click on this to see the results. Yes, so if you turn on or open your space claim under this geometry, so it will be updated with this optimized thickness, which is 1.8 mm. Right, so I'm turning on space claim. Then if you can see here, right, so your group's thickness here now is updated with 1.8. If you can measure it, yeah, this edge also it is 1.8, right? So that is being updated. Then if you go to mechanical, starting mechanical, then the analysis result also being updated with this 1.8 thickness. Right, so that's the result. The deformation is 0.238, which is slightly larger from just now, which is 1 and 2 mm thickness is 2.21. Then the stress also increased 984, but then it fulfilled the what we call design constraint, which is less than 0.3 mm. Then at the same time, our mass, which is now is the optimized one, which is 0.0036 compared to just now with the 2 mm thickness is 0.004. So this is what we call the optimum design, and this is the entire flow of from topology optimization to find out the best optimum shapes, then use space claim to build a model based on the topology optimized model. Then from there, we perform further on parametric optimizations to minimize the weight at the same time to ensure it fulfills the design constraint of less than 0.3 mm total deformations. Then this is the entire full flow of procedures. Thank you.